Hello everyone, in this work, we would like to introduce our work to you now, HARDVS, Revisiting Human Activity Recognition with Dynamic Vision Sensors, which was published at the top international conference AAAI 2024. The mainstreams of human activity recognition algorithms are developed based on RGB cameras, which usually suffer from illumination, fast motion, privacy preservation, and large energy consumption. Meanwhile, the biologically inspired event cameras have attracted great interest due to their unique features, such as high dynamic range, dense temporal but sparse spatial resolution, low latency, low power, etc. We can see that the data recorded by the event camera consists of a quadruple X, Y, T, P, where X and Y represent spatial coordinates, and T is the timestamp, and P is the polarity of brightness variation. On the right, you can see the recording method of the event camera. Unlike RGB cameras, event cameras only record pixels with changes in brightness in the scene. Therefore, for a rotating disk with black dots, the event camera will only record the trajectory changes of the black dots. As it is a newly arising sensor, there is currently no realistic large-scale dataset for human activity recognition. There are currently some existing datasets for human action recognition, such as DVS gesture, ASL-DVS, DVS-128 gate day dataset, and daily action DVS dataset, etc. DVS gesture only includes 11 hand gesture categories from 29 subjects under 3 illumination conditions. ASL-DVS only contains 24 classes correspond to 24 letters AY, excluding J from the American Sign Language ASL. DVS-128 gate day dataset was obtained by playing and shooting the dataset CASIAB on the screen. CASIAB is an RGB video dataset. This is a common way to obtain event datasets in the past. There are 124 subjects, and the gate data was captured from 11 views. Daily Action DVS dataset has 1,440 recordings of 12 daily actions. The dataset is captured by a DVS camera with 2 different lighting conditions and 2 different camera positions. These datasets have shortcomings in terms of scale, types, and acquisition methods. Considering its great practical value, in this paper, we propose a large-scale benchmark dataset to bridge this gap, termed HARDVS. The HARDVS dataset is collected with a DAVIS-346 camera, whose resolution is 346 multiplied by 260. From a statistical perspective, our dataset contains a total of 107,646 video sequences and 300 classes of common human activities. When constructing the HARDVS benchmark dataset, the following highlights are considered: 1. Large scale, 2. Wide varieties, 3. Different capture distances, 4. Long term, 5. Dual modality. Our dataset considers multiple challenging factors which may influence the results of HAR with the DVS sensor, such as multi-view, multi-lighting, multi-motion, dynamic background, occlusion, and long action duration. With the aforementioned characteristics, we believe our HARDVS dataset will be a better evaluation platform for the neuromorphic classification problem, especially for the human activity recognition task. In addition, we devise a new event-based spatial temporal transformer approach for event stream data learning. As shown in figure, the proposed ESTF architecture contains 3 main learning modules: 1. Initial spatial and temporal embedding, 2. Spatial and temporal enhancement learning, and 3. Spatial temporal fusion transformer. Specifically, given the input event stream data, we first extract the initial spatial and temporal embeddings respectively. Then, a spatial and temporal feature enhancement learning module is devised to further enrich the event stream data representations by deeply capturing both spatial correlation and temporal dependence of event stream. Finally, an effective fusion transformer block is designed to integrate the spatial and temporal cues together for the final feature representation. 3 datasets are adopted for the evaluation of our proposed model, including NCalTech 101, ASL-DVS, and our newly proposed HARDVS. The widely used top 1 and top 5 accuracy are adopted as evaluation metrics. We retrain and test multiple state-of-the-art models for future works to compare on the HARDVS benchmark dataset. We can see that our model performs well on the ASLDVS and NCalTech 101 datasets, and also achieves competitive performance on the HARDVS dataset. From the experimental results reported in the ASLDVS and NCalTech 101, we can find that existing event-based recognition datasets are almost saturated. The newly proposed HARDVS dataset can bridge this gap and further boost the development of event-based human action recognition. In addition, we conduct extensive experiments to analyze the contributions of each key component and the influence of different settings for our model. The upper left table analyzes the roles of different modules in the model. The three images on the upper right respectively show results of different input frames, transformer layers, and patch sizes on the dataset. The lower images show that the feature distribution of our baseline and newly proposed ESTF on the HARDVS dataset in Fig A, B, and confusion matrix of baseline ResNet and our model on the NCalTech 101 dataset in Fig C, D. As a conclusion of this tutorial video, we propose a large-scale benchmark dataset for event-based human action recognition termed HARDVS. It contains 300 categories of human activities and more than 100K event sequences. More than 10 popular and recent classification models are evaluated for future works to conduct comparisons. In addition, we also propose a novel event-based spatial temporal transformer (ESTF) that conducts spatial temporal enhanced learning and fusion for accurate action recognition. Extensive experiments on multiple benchmark datasets validated the effectiveness of our proposed framework. We hope the proposed dataset and baseline approach will boost the further development of event camera-based human action recognition. In our future works, we will consider combining the color frames and event streams together for high-performance action recognition. Our dataset, source code are all open-sourced and can be found in the following GitHub highlighted in red. Thanks for your attention.